Hi guys, this video is an application of Sylow's theorem, but we do not discuss the Sylow's theorem here. First theorem we have is, for a prime number p, every group G of order p square is abelian. We have the proof here. Let A be an element of G such that A isn't the identity element. Then if G isn't cyclic, then G isn't generated by any of its element, so the cyclic group generated by A isn't the group G itself. Now p is prime is given to us, so the only number dividing p square is p itself other than 1. So the order of cyclic group generated by A is p. Now we have, by first Sylow theorem, the subgroup generated by A is normal in some subgroup of G of order that is greater than the order of group generated by A. But we have the only such subgroup of G is G itself. So the subgroup generated by A is normal in G. Now again, let B is an element of the group G such that B does not belong to the subgroup generated by A. Then we have the subgroup generated by B is not equals to the subgroup generated by A, and the subgroup generated by B is normal in G with the same argument as previous. Then we have the join of the subgroup generated by A and generated by B is a subgroup of G properly containing the subgroup generated by A. This group, it properly contains the subgroup generated by A. But because p square is only divided by p, we must have this entire group equals to the group G itself. But we have the subgroup of join of group A and B is isomorphic to the group A cross B, which is abelian. Therefore, the group G is abelian. The second theorem we have is, if H and K are finite subgroups of G, then the order of Hk equals to the product of order of H and K divided by the order of H intersection K. We have proof here. Let the order of H is R, and of K is S, and of H intersection K is T. Now suppose any two elements of Hk are equal. Suppose H1K1 equals to H2K2. This implies H2 inverse H1 equals to K2K1 inverse. That equals to X, suppose. Now H2 inverse H1, it belongs to H, and K2K1 inverse, it belongs to K. So X, it belongs to H intersection K. This shows H2 equals to H1 X inverse and K2 equals to XK1 from this line. So H2 can be written as this form and K2 it can be written as this form. This shows each element in Hk can be written as many times in the form of Hiki as many times there are elements in H intersection N, that is T times. So we must have the number of elements in Hk equals to Rs, product of Rs divided by T, and that equals to product of order of H and K divided by order of H intersection K. So we must have the order of Hk equals to product of order of H and K divided by the order of H intersection K, and this proves our theorem.